Hey everybody, this little video lesson is going to cover concentrations and how to calculate between them, and it's one of your learning objectives, so pay close attention. So in this class we're going to cover 5 different ways to express concentration, at least on this test, and I'll expect you to know what each mean and how to use each one and how to convert in between them. The first one is the most popular, at least for academic chemistry, and that's molarity. The reason I qualified it as academic chemistry is because it's got one very serious limitation that keeps it from being used in lab scenarios outside of academic chemistry, and I'll explain that here in a little bit. Now, the abbreviation for molarity is, of course, capital M, and it stands for moles of solute over liters of solution. Here is that it's total liters of solution. That includes the volume of the solute and the solvent added together. And so when you're trying to create something with a specific molarity, it's important that you don't add the final volume of solvent and then add the solute on top of it, because then what happens is the solute adds volume to the solution, and so you actually have less concentration than you think you do. Now, the next one, which is used more for practical chemistry, is called molality. And its abbreviation is a lowercase italicized m, and the reason it's italicized is to keep it from being misconstrued as lowercase m as meters. But molality is moles of solute per kilograms of solvent. Now this one is used more for practical chemistry and industry and likewise, because the difference between these two, molarity and molality is based off of the volume, where molality is based off of the mass. And there's one thing that affects volume and not mass, and that's temperature. If you increase the temperature of a solution, what you're doing is actually decreasing its molarity, because as the solution increases its volume, keeping the same number of moles of solute the same, it actually becomes more dilute. Whereas if you increase the temperature of molality, it doesn't affect the concentration of the molality at all, because mass is not temperature dependent. And because of that, it's used most likely in industry, where temperature can be a factor, and if with changing temperature, molality doesn't change, but molarity does. That is why a molarity is always assigned at a specific temperature, because as the temperature changes, the molarity may change. But we use it for academic chemistry because it's easier to use in stoichiometric situations. It's also easier to use in other aspects of chemistry. In essence, it's just easier to calculate with. Now the next two are very similar. They are percent by mass and percent by volume. Percent by mass is defined as grams of solute over grams of total solution. And that makes sense. If somebody tells you that something is 5% by mass, that means for every 100 grams of stuff, 5 of them, 5 grams is solute, so 5%. It's the same with volume. If you've got percent by volume, it's the same. It's milliliters of solute over milliliters of total solution. And these two are quite useful in nutrition circles when you're talking about, say, for example, vinegar is 3%, which means it's 3% by mass. It's 3 grams of acetic acid for every 100 grams of vinegar. Alcoholic beverages are also measured in percent of alcohol content per ounce or something like that. So you may say it's 5%, which means it's 5 milliliters of solute or ethyl alcohol for every 100 milliliters of total solution. Percentages are easier for the everyday person to wrap their minds around. Nobody really talks about moles and kilograms and liters, I guess. Moles is really the sticking point with a lot of people, so molarity and molality are common in actual chemistry classes, where percent by mass and percent by volume are thrown around by the everyday person. The last one that I want to talk to you about is called mole fraction, and the reason we talk about it is because there's a very important property here coming up in the next class period where we're going to need mole fraction to do the calculation, and so let's talk about it. Well, as you probably would imagine, it's just the fraction of moles, but here it is. Mole fraction is abbreviated as a capital X, and it's calculated as the moles of the solute divided by the total moles. Now that's the mole fraction of the solute. You could also express mole fraction in terms of the solvent, and so it would look a lot like it, but the numerator would be moles of solvent over total moles. But either way, you would let the person know ahead of time that you're looking for the mole fraction of the solute or the mole fraction of the solvent. it's important to note that the mole fraction of the solute plus the mole fraction of a solvent of any one particular solution would always add up to equal 1 or 100% or whatever you want to call it, 1 over 1. Because if you think about it, the moles of solute plus the moles of solvent would equal the total moles of the solution. So you've got 1 over 1. Oftentimes, mole fraction is expressed as moles, letter N, of substance 1 over NT. And we saw mole fractions back in the gas laws chapter when we talked about the pressure to moles conversion. This next slide has a couple of practice problems which helps us convert and helps us practice converting between the different concentration calculations. So let's tackle each one at a time. So you're given 36% HCl by mass, and you'll be asked to calculate the mole fraction of the HCl in the solution. Remember, mole fraction is moles of HCl over total moles of the solution. And since this solution is aqueous, then the solvent is water. So if I rewrite the mole fraction in this form, I'll say moles of HCl over moles of HCl plus moles of H2O, because that denominator is the total moles of the solution. So that's my final goal. Now I need to take the 36% by mass and calculate mass to moles of the HCl and mass to moles of the water. That's easy enough because we know molar mass. 36% by mass means that there's 36 grams of HCl per 100 grams of total solution. And that solution is made up of HCl plus water, so we can do a simple subtraction and say, well, if there's 36 grams of HCl, there must then be 64 grams of H2O. Now what I'm going to do is simply take the grams of HCl and the grams of H2O and solve for moles of each. If I take 36 grams of HCl and divide by the molar mass of HCl, which is 36.46, I get 0.99 moles of HCl. If I take the 64 grams of H2O and divide by its molar mass of 18.01, I get about 3.55 moles of water. So the last thing I need to do is take that information and plug it into this original mole fraction formula and figure out what I need to do. So I'm going to take the 0.99 moles and divide by 0.99 plus 3.55. And the answer I get is 0.2175, rounded to 2 sig figs is 0.22. Now, the units of mole fraction is that there are no units. You're simply taking moles dividing by moles, so you're just simply looking at a decimal point, something less than 1, because you're comparing the moles of one of the parts of the solution compared to the total solution, so it should always be less than 1. Now part B is asking us to calculate for the molality, and if you remember from the last slide, molality is moles of solute per kilograms of total solvent, not solution, but solvent. Now I can use information from the first one to really calculate molality. First of all, moles of solute. I had 36 grams of HCl, or 0.99 moles of that solute. I already did that calculation, and so I start with the 0.99 moles of HCl. Now the kilograms of solvent, going back to this part right here, we had 64 grams of solvent in this original solution, and if I simply move the decimal point over 3 to the left, I have 0.064 kilograms of H2O. So now I have the ratio set up. All I need to do is punch that into my calculator, and I get 15 molal. It looks like 15 meters, but it's really 15 molal. Now the last one asks me to calculate the molarity of the solution. And I need molarity, remember, to be moles of solute, which again is going to be 0.99 moles, but I need to get that over liters of solution. In order to convert between molality and molarity, I need to know the density of the solution in order to do that, because that's going to help me calculate from grams to milliliters. The only way to get from grams to liters or grams to milliliters is using a density. Without it, it cannot be done. Now, I don't want to use the 64 grams of water or the 0.064 kilograms of water from part B, because remember, this is liters of solution. And if you remember back in part A, I started with 100 total grams of solution. It was 36% by mass, which means 36 grams of HCl per 100 grams of total solution. So I'm going to stick to that 100 grams of solution. And if I use a quick dimensional analysis, the density of this solution is said to be 1.02 grams per milliliter. So I put the 1.02 grams on the bottom per 1 milliliter on top. So I do that quick division, and it gets my volume down a little bit. It's slightly less than 100 milliliters. In fact, you get approximately 98 milliliters. Now I need to convert that to liters because in molarity I need it to be in liters. So I move the decimal point over to the left 3 times, and now I have everything I need to solve for molarity. The moles of solute, once again, is 0.99 moles of HCl, and my liters of solution is 0.098 liters. And so I have just about 10 molar. In fact, if I do the math and round to the correct number of significant figures, that is indeed the final answer. So let's tackle this final problem. I take a look at the problem, read what I have available to me. I have a density, which is going to be helpful when calculating from grams to milliliters, because eventually I need to get a molarity. Molarity, remember, is moles of solute per liters of solution, so I'll use that density to get my molarity. I really want to tackle this problem in really 2 parts. The first part is going to take my solute and convert it to moles, and that's going to be pretty easy using a molar mass step. And the second part is going to be using and taking my solution and converting it to liters. That one's going to be a little bit more tricky. So let's start with the easy part first. I begin with 5.0 grams of toluene, or C7H8. Now, using a simple molar mass step, I can calculate the moles is equal to 1 mole on the top and 92.14 grams of that stuff on the bottom. So after dividing that, you get 0.054 moles of C7H8. Now remember, I need the volume of the solution, and so I need to factor in both the solute and the solvent. So I have the mass of the solute and the mass of the solvent, and if I add 5 grams plus the 225 grams of solvent, I get 230 total grams of solution. The most common mistake I would see with this one is students would take this density and simply convert the grams of benzene to liters of benzene and divide by liters, but this is not liters of solvent, this is liters of total solution. So you got to add the masses together first and then use the density to calculate the volume in milliliters and convert to liters. So I take that grams and I simply use the density 1 milliliter on the top, 0.876 grams on the bottom, and that'll give me 262.5 milliliters. And if I move the decimal point quick over 3 times to the left, I have 0.2625 liters, but I want to round that answer to the 3 significant figures because my original number is in 3 significant figures. So it's 0.263 liters, and now I'm going to take that and I'm going to plug it in right up here. So I take 0.054 moles of the solute and divide by 0.263 liters, and I should get a molarity of 0.207 molar, and that's my answer. So that takes care of this little video lesson on concentration calculations. Thanks for listening.